I'm just going to let my friends know that I'm alive. Well, I need to tell you really, because we've got a group. It's on RWG Research, that's Russ Grease, and this is where we tend to hang out. So Russ has got a Discord chat where we all go to talk about free energy and stuff, but it's been kind of dead lately. But I'll bring this menu up so I can show you what I'm seeing. Right, well, there's a chat, and unfortunately it's invite only, but you'll have to go to his website to get him to invite you or something, because it's just to keep out the trolls and all that. But if I can just bring this up on our webpage, it's worth you knowing about this group, because I'm not just doing this on my own. I mean, I'm doing it on my own, it's my own design, but I am sharing with the community with Russ Grease at RWG Research, and he's really well known in the free energy research circles. So I wanted to go over this a little bit, because let me just see if I can get his website up on here, because I don't think I bookmarked it on here. Come on, the phone's slow as well right now. It's ridiculous. Oh dear, let's see. Come on. Right, you need to go and check out Russ's website, and see if I can get this closer. And there's a community chat on the website which you can join up to. Russ runs the free energy research forums. I don't know if you can read that. It's probably blurry. I've set the stream to 1200 by 720 right now. No, 1200 to 700 at the moment, because I'm doing a test with high quality resolution, and it's so anyway, go to check out Russ's website. He's got loads of fascinating free energy research on there, and if you go to the website, you'll find there's a community chat thing on there somewhere. I'm not used to using it on the phone, so it's a bit difficult. Let me just see. Is it under this? Yeah, there's a. It's got a lot. It's got home. It's got a forum. There's a live stream. There's. Oops! I've clicked something now. Uh-oh. I'm gonna go back again. If you go on. There's a menu down here for useful links. I think it might be that one. Let's see, is it this one? I think it might be under here somewhere. Oh no, maybe not that one. But anyway, under the... I'll just go back. Oops, I'm clicking on stuff by mistake. I think it's under forum. Russ at the moment is trying to raise some money to help kids this Christmas, so if you can pass the message on to people, he's actually doing fundraising with his church to raise money to help kids this Christmas, so it would be worth you passing the word around. Yeah, there is a chat thing somewhere on there where you can go and find the information. Just go to home. There is something on there for Discord chat. I don't know where he's put it. You have to look around the website. Right. So what he basically does is he duplicates previous inventions and things and tests them out. So anyway, as I was saying, I will get back to my project in a second. I just wanted to let you know about that because kids are going to have a pretty tough Christmas this year, what with the coronavirus and everything. It's bad enough for everybody really, but just give me a minute. Right. What the heck? I don't understand why it's showing the preview for the previous video for the new stream. Doesn't make sense to me. It's showing the... Oh, it's obviously with the live stream that I'm doing right now, which is a... I'm just baffled about that. It's just, oops, I went to close the chat. So anyway, now the interesting thing about this is that when I'm sending in the right frequency, and we're actually only supplying this device with 150 milliamps of drive current at 30 volts at oh, I better put my oscilloscope on actually. I'll let that warm up. I need to tell you the details about what's going on, but there is a bit of misconception that this is already under load, but it's not actually, because if I disconnect, I can't do it easily now actually, but if I disconnect the actuator coils from the output side, it still uses the same small amount of current. So you just have to get it in resonance. Once the unit's in resonance, like it is at the moment, it's only drawing 70 milliamps at 30 volts, but pulsed at 190 microseconds. So we're sending a pulse. We're sending a pulse of 190 microseconds into a 1 microfarad capacitor that's on the input side, which absorbs that energy and turns that into an RMS AC waveform, which then drives the 4 actuator coils, because there's 2 actuator coils on each side. Those coils are in resonant harmonic frequency, as best as I can get them at the moment, because there's a mismatch between this pair of coils and this pair of coils. They're not perfectly matched. It's because of that we're consuming as much power as what we're doing right now, because even so. But when I remove the load, if I take the load off completely and there's no longer power coming out of this thing, my input current shoots way up. It goes up to like 400 milliamps. I don't know if you can actually. Well, we'll look at the high side because it's easy to see. It's at 70 milliamps right now. But if I take the load off this thing, oh, hang on. Alright, got the right wire. No, I've got the wrong wire. Oops. If I take the load off this thing, now look at that. The input current now has gone up to 150 milliamps, Right, look at the waveform over there. It's got up to 67 volts peak to peak. RMS, cycle RMS 24.4 volts. We're actually drawing 150 milliamps on the input now. That's with no load. Now, I put the load back on. Oh, did you hear that crack then? That was juice. So with the load on, our input current has got dropped way down. And the greater the amount of load I can put on this thing, the less input power we actually use. And I found that out simply by the fact that when I replace these corners with the new corners, so here's one of the old corners, which was just basically a ball bearing, which is a steel ball bearing with a mouse ball. Actually, these are mouse balls, but they're magnetic with a magnet on there. You can see these steel balls with a rubber coating on them, and two ferrite rings, and there's a gap between the ferrite ring and the ball bearing. There was a gap of about 3 millimeters or so. And on both of these were very lossy. I lost quite a lot of flux on these corners. So when I replace them with a solid steel lamination assembly, which I got laser cut, which thank you to the ones that donated to help me with that, because it cost me about £66 UK sterling. So once I got those cut and I fitted them in the four corners, I'm actually using less input power, and I've got more output current and output power than what I had previously. Because at the moment on this meter it's hard to see it. Let me go and get the other digital meter. It'd be a lot easier to see what's going on. Where have I put it? Where are you? Oh, there you are. Let's hook up this other meter, which is a lot easier to see. So I'm going to stick this on the 400 milliamp range. I'll stick that there. I'm going to unplug these leads because this is hard to see. Right. I'll stick that on. I'm going to go milliamps. Now you can see these. Let me just get the light right. You should be able to see that's 51.4 milliamps DC going into them. I think you can see that. You should be able to see that pretty well, actually. I need to check the preview on the YouTube channel to make sure it's coming up okay, because it's hard for me to tell. Right, so I've actually got it reversed. I need to put these leads in the other way around. It doesn't really matter, but right, that's the output current. A lot easier to read than it is on the analog one. So this thing is actually, it's climbing. Actually, the current is going up, and the input current is still at 70 milliamps. I don't know. There's a wire in the way. It must be. Is it this one? Yeah, I think it's this wire that's blocking our view a bit. I'll try and. Oh, I need to put something on there to hold it from getting in the way. I'm going to put my nail clippers over this thing to hold it down. That's better, maybe. Yeah, because the wire was just sticking up. Right, so we're at 30 volts, or 29.99, it's near enough 30 volts, and 70 milliamps pulse at 190 microseconds. Our output is, well, I've got a load on this right now. I'll turn that meter off because that's with the load on it. This is with the load on, and it's at 10.4 volts on this one coil. That's this coil down here, which is It's difficult to see. Let's just get some. Where's my torch gone? So that coil down there is the one that's ideally tuned, really. This other coil is producing higher voltage but less current, and these other two coils are also sending power. They're all going to individual rectifiers. So I've got this bridge rectifier on my old generator. I've just connected directly to these bridge rectifiers to save me time. So I've got this bridge rectifier connected to one coil, this bridge rectifier is connected to the other coil, this bridge rectifier is connected to the third coil, and one coil on here is not connected to anything because the voltage on it on the output is too low to actually do any good. So I've just got a capacitor across that coil. Which one is it? I've forgotten now. I think it's this coil here. This coil here is not connected to the output because I've just got the oscilloscope on it. So that's the yellow trace that we're looking at. So on the oscilloscope, the yellow trace is peak to peak 27.6 volts. So we're measuring 27.6 volts peak to peak on the yellow trace, which is not in use. That's why there's no flat on the waveform. It's just a perfect sine wave, and I'm using that as a reference. I could actually connect that coil to one of these other rectifiers and would see even more output. I could actually do that now because we're seeing a decent amount of peak-to-peak voltage on it now than I used to do. There's a cyclic RMS on it of 8.8 volts, which is pretty good. But the blue one is even with the blue one under load, the blue channel under load is producing a higher voltage of 28 volts. Cyclic RMS of 11.6 volts. So the blue channel under load is producing more voltage and more current than the yellow channel is producing without any load on it. So that's part of the reason why I haven't put a load on the yellow channel, because the coil is smaller. Well, it's thicker wire, but it's actually doesn't have enough turns to produce the required voltage. Now, how can you make use of something like this when the actual device uses less input current when it's under load? You would think, well, the trouble is that once the load is lighter and there's less of a load on it. I'm using a paintbrush to point, by the way. So when the load is lighter, what you need is what you call a parallel regulator. What a parallel regulator, I'll see if I can pull it up on my browser, is not the same as a series regulator. A parallel regulator is like a clamp that you put across the output, and it keeps the output voltage. I'll see if I can show you a circuit. See. Right, if I get this schematic up, I can show what the difference is. A series regulator is something that produces a voltage, a stabilized voltage, and it doesn't apply a load to the actual. It produces a minimal load to the actual output voltage when it's been regulated. But a parallel regulator produces a huge load to the supply voltage when there's no real load on it. So it basically clamps that voltage and keeps it low until the load that you apply to it is greater than the parallel regulator is, and then you can draw your power out. Oh god, I hate these flipping pop-up boxes things. Right, so a parallel regulator, they're using chips. I was really looking for discrete circuit. It's a lot easier to understand. flipping heck. I hate all these microchips. You don't need all that. You just need discrete. I want a discrete. Just give us a sec. Discrete. Right, this should be the one. Sorry, it's taking a while to load. I'm hoping this is a discrete one. There we go, there's a discrete diagram. Now, what I can do is I can maybe move the camera across to the screen, or better, I'll just blow this up. Let me just expand this. Oops, a bit too much. I hope you can see that, but using a discrete single transistor, that's a series regulator. We don't know about series regulators. I want the parallel one. Where is it? This is it. It's also called a shunt regulator, but it's a parallel regulator. It's a shunt as well. Right, here's a shunt regulator. Let's just stick with that then. So this is a parallel regulator. So the way that works is it shorts out the load when it's not being used. So what you have is a Zener diode. Let me just click on it. You have this Zener diode here, right? And that Zener diode turns that transistor on, which shorts out the load, which is on this rail and on this rail, shorts it to ground. So it holds it at that regulated voltage of whatever the Zener is. So let's say it was a 12 volt Zener diode. So that would shunt the voltage to ground and stabilize the output voltage to whatever it is you wanted. So you might have 12 volts on the output. But when you put a load on, say you wanted to run some LEDs, and them LEDs consume more power than the shunt, this thing here, this transistor. Once it consumes more power than that shunt is actually shorting to ground, then the shunt regulator basically does less work. So the shunt regulator would actually run cold once you had a real load on the output. So when you're not actually got a load on the output, the actual shunt will create that load to keep the output loaded down. So you could buy something like this generator that actually uses less power when it's under load. It's more advantageous to bleed that energy away and ground it when you're not using that power, because otherwise your input current goes way up and you end up consuming more power when you're not using the power from the generator, if you understand what I'm saying. So let me just get rid of this scribble. So if I could just zoom in again, because it says me moving the camera, if I just zoom right in, you can see the circuit. It's very poor resolution actually. I wonder if I click on that image, will I get a better resolution image? Yeah, that's better. Right, that's a lot better, a lot clearer. So there's the circuit of a parallel regulator, or shunt voltage regulator. They call it shunt or parallel. It doesn't matter, that they've got different names for it. But so that's the sort of circuit you would use on the output stage for something like this. But as I say, there's a lot of work to do with it at the moment. I've got more tweaking to do on my output coils. I've got to bring them all so that they're all producing a decent amount of RMS current and voltage to do what I want it to do. If you've got a coil that's wound to produce a much higher voltage, it's going to produce less current, so you end up with less benefit, but it gives you a higher headroom for small amounts of current, but it gives you no headroom when it comes to the fact that you want more current to charge up a battery, for example. You might want to optimize the amount of current that's being sent into a battery. Yeah, so I was just looking at, our friend posted something on the on his thing. He posted the Porky Pig. I don't know what that's all about. So anyway, so I'll get rid of that. How do I get that image to go away? Where's the escape button? So anyway, the series regulator doesn't consume as much power when a series regulator. The difference with a series regulator is it's in series with the voltage and current that's coming in. So the power is coming in this direction, and the series regulator and the Zener diode here, down here, that will determine how much voltage comes on the output. But when there's no load on the output with the series regulator, there is actually basically no load on the input side as well. So it's a different way of doing it. When the greater the load on the output of a series regulator, the greater the load on the input of a series regulator. Whereas the shunt regulator or parallel regulator will have a greater load on the input side when the output side is non-existent. So you get the idea with that, I think. So I wanted to talk about that because it's very important about how to make the best of the power and optimizing a transformer like this when you're trying to draw power from a device that actually consumes less power when it's under load. You basically want to keep it always under load, right? Alright, well, I've covered that. My live stream's glitching out on me again. I'll make sure there's no. But you might have Sorry, I'm a bit a long way from the microphone. I'm sorry about that, but that's because of the noise. I don't know if I can move it closer without the noise getting louder again. I don't know. This thing here, this transistor. Let me just try that. Consumes more power than that shunt is. See what happens. Is it going to get louder? It does less work. So the shunt regulator would actually there's a delay. You had a real load on the output. So when you're not. Let me just check this. I'm not sure there's no. But you might have sorry, I'm a bit a long way from the microphone. I'm sorry about that. But that's because of the noise. I don't know if I can move it closer without the noise getting louder again. I don't know. This thing here, this transistor. Let me just try that. Consumes more power than that shunt is. See what happens. Is it going to get louder? It does less work. So the shunt regulator. There's a delay. You have a real load on the output. So when you're not. Yeah. I want to bring the microphone closer to me, but unfortunately this thing's throwing off so much EMF, electromagnetic field, from that signal that it's just completely wiping the audio out. But anyway, so we're actually doing pretty well, really, considering, because at the moment the actual current going out is still at 51.5 milliamps. And our output voltage at the supercapacitor is up the top there is about 10 volts. Well, you can see it on this meter here, it's about 10 volts. So that's not bad, really. It's a bit of an improvement to previously, because when I was doing these tests previously, at around about 10 volts, this current on the output side would have dropped to about 30 milliamps. It was around 35, 40 milliamps. We're actually seeing more current there going out than what we did before, but it's still not ideal, and that's simply because my output coils aren't optimized. They need to be optimized a bit more. So yeah, I think I've covered everything. I can't think of anything else really, apart from the fact that I'm just fed up with trying to go live on YouTube and struggling for half an hour just to get it to go live, which is really ridiculous, and it's kind of putting me off, to be honest with you. You might not expect to see as many live streams, I don't know, because it's just harder for me to do that, because I've got to fart about going on the virtual machine and logging in and clicking the live button, because it's not working on the phone like it used to do. So I used to be able to just get my phone over here, and I'll show it on me. Right, there's my phone, right. So, oh, I've got a comment on here. Right, I just want to show you what I used to have to do. I used to just exit my chat menu. I used to click on Streamlabs like this. Right, this is how easy it used to be to go live. The menu comes up. I would click on the live button like that, and then I'd get this thing come up, it said persistent. I'd just click on that and I'd go live. That was it, no trouble. I used to be able to go live just like that. Can you do that now? No, I've got to scroll all the way down this flipping menu. It says create event, click on that, creates a new event, and then it makes this flipping new video live stream which says unlisted. It says it's unlisted, which is not even friggin' listed. And not only that, it doesn't go live. I've got to go on the flipping virtual machine, log on to Google or YouTube, and click a go live button before it goes live on my phone. Is that any fun? No. And is there any wonder that I've been swearing and cursing lately? So you can understand why I get upset with YouTube, because YouTube has just been a real pain in the butt lately. Making life not easier but harder. I mean, this is a phone, it's not XP. It's got what do you call it installed on it? It's got what do you call it? I forgot what you call it now. That robot-y thingy operating system, you know, I forgot what you call it now. You know which one I mean. Can't think of the name of it. But it's up to date. The freaking thing's up to date, and it won't work. So anyway, you know what I think is, you see, it's because I'm charging up the I'm sending the output from this generator through all these wires, and it's travelling through all these wires to my oscilloscope. It's travelling up that lead up there all the way up to my solar supercapacitors to charge them up. That's why it's making so much frigging noise on the microphone, because it's like a big antenna. No matter where I move the microphone, it's picking up this signal, and it's really annoying. But it's actually quiet. I can't hardly hear a thing. I can hardly hear anything, but it's electromagnetically picking it up, you know, like an antenna radio signal. It's picking it up like a radio signal instead of an audio signal, and so it's extremely annoying and irritating, I know, but I'm sorry about that. Anyway, I'm tired. I can't really show you much more at the moment, because, as I say, I want to get these. Oh, I can show you a bit more. The concentric magnet arrays, I can show you a bit more detail about them. I'm going to go and grab another one. About, was it 4 years ago? About 4 years ago I was working on these concentric magnet arrays. This is a 6mm one with a ring around it. It's got those steel laminations in there. Got a bunch of steel laminations. I also had laser cut in this arrangement, and it's basically alternated north-south all the way around. Here's another one. This is probably easy to show you, because the way it works is by subtraction and repulsion. This one's only got 4 magnets in it, so it's got basically north-south and north-south, and it's not fully populated. Actually, let's populate it. I've got some more magnets down here. So I've got some of these 20mm disc magnets. Take one of them out. It's got to be alternated, so it has to be reversed for that one. So stick a magnet in here like this. That's populated now. Flip it over. Stick it in the next slot. Get another magnet. Flip it over like that for the next slot. And get another magnet. Flip it over for the next slot. So alternated. So that's fully populated now with 8 concentric magnets, so that it's alternated like this. Right, so what we have now is a subtraction and repulsion ring. So normally there's, if you stick a steel ball in the middle, actually I have a bit short of steel balls at the moment. Let's stick one of these in. Stick a steel ball in the middle there. There's no magnetic pull on that whatsoever right now. It's dead until it's biased. So we get another set of magnets, and let's bias it underneath. I just need to get this right around. So we get our magnets and we bias it. Now when you get to a certain distance, it feels like there's nothing pulling and nothing pushing at all. When I hold this magnet in this position here, it's not pulling, it's not pushing, because it's balanced, because some of these magnets are being pulled towards this magnet and some of these other magnets are being deflected by this magnet. So at this point here, there's no attraction, no repulsion. However, if I hold it at that right distance without it flying out of my hand by letting go or something, if I hold it at the right distance, oops, my ball just fell on the floor. Oh, what's that done? We actually have a deflection on this side. Oops. Right, so we have a deflection here, even though you can see on this, these are just magnets in a tube with 2 ball bearings. So if we hold it about there, we actually have a deflection on these magnets, even though these magnets over here don't feel anything. There's no attraction and no repulsion, so we're in this sweet spot area. But if we go a bit closer, we start to have a pull. We actually start to have a pull force on this side, whereas this side is pushing. You see, it's the opposite. Right, do you understand that? So this side is pulling in to this array, look. I'm actually holding it in like this. It's pulling. This is pulling, yet the other side is pushing. Do you see the opposite? It's doing the opposite effect. We have inverted the effect of the magnetic field, because what's happening on this side, it's pulling, right? It's actually holding the ring up against these magnets, and on this side it's pushing. So that's inverted. So every effect on this generator is reversed. So when you have a load on it, you actually have less input current. Do you understand what I'm saying? We actually draw less input on the input. There's less current consumption on the input when we have a load on it, because it's reversed. Because this is pushing this magnet away, while this is actually pulling. When in theory, if I put these two together, this would be pushing and this would be pushing equally against each other, but like this they are. So like this they are equally pushing against each other, because, but when I put this thing in between, this is pulling and that is pushing, so it's inverted. So basically, if you can imagine a waveform, the cycle of a waveform, it's like the waveform is inverted, so the lens effect is also inverted. Anyway, that's explaining it. Right. So that's it for today. I also read the smaller rings as well, these, and the smaller rings go inside the big rings, and just to give a little bit more leverage to improve these, they've got steel washers in there which I actually cut, but these particular ones have got little where have I put them? Well, little bits of steel like this, but a little bit thinner and longer, and they run down the sides of the actually I've got one over here somewhere, if I can find it. Well, this one hasn't got the steel rods in it, but this has got the steel welding rods on the middle, and it's got another concentric on the outside. It's got a thinner concentric on there. Same sort of thing. If I can get this lined up right, get this level. It's a lot weaker, but this is designed to go inside that. So what I do is I pop this out like this. Oh, actually it's stuck. It's stuck. I can't get it out. It's been in there for a few years. I don't want to break the ring. It's really stuck in there. Ah, it's coming. Damn thing. Trying to get it out. Right. So I've taken the core out, which is these steel washers, half washers that have been cut and filed. Take that out. There's my ring with all magnets in it. Let's get this lined up right. I need to see. Hard to tell which is what. Oh, just a minute. South. And that's south. That wants to be like that. And this fits in here like this. Right, there we go. I've put the new ring inside that big ring, and now we can do the same thing as before. It should be more efficient now. Where's my magnets gone? I've put them down somewhere. Ah, they've rolled away. I've just lost a bunch of magnets, I think. What do I do with them? Oh, it's alright, I've got another set here. Oh, I see what they are. Right, get this right way around. Oops! See that? It deflected, even more efficient now. Take it away. If I push it, take it here. Look, it's even more effective now because there's this middle ring as well. Pull it back. Flip it. Reverse pull. Now it's subtracting. This is still pulling, by the way, on here, and now that one's pulling. So this is pulling. This is still pulling, but this is deflecting now. You see? So if I put my fingers like this whole thing is pulling up against the magnets, because there's nothing, I'm not holding this thing at all, it's just being pulled up by the magnets. I'll show it, I mean. Right, are you watching? It's lifted up by the magnets. So this is being attracted by the magnets, but on the other side it's deflecting. Oops. Right, so that's deflecting. This side doesn't see that because it's engaged with these other ring magnets all we're doing is subtracting the field, which is cancelling out the field on this side, so that this side can actually do some work. So we're subtracting the field of magnets, which normally would cancel this side out. So it's like a big firewall. And I did some tests a few years ago on a YouTube video where I was doing a weight test, and the amount of force required to actually pull on here, it turned out that I was gaining a mass of weight gain on this side because it could hold a lot more on this side than what I was actuating on this side. So when you put a steel ball on it, I don't know where that ball's gone now, but that ball was still attached for quite a long time. If I take this magnet away, if I just lift this up, it falls off now, look. I'm cutting myself on these bits of metal. I had a big heavy piece of, let me find something much bigger. So I've got these pliers. Now look, we're holding a pair of pliers now with this. So now I'll just slowly lift this magnet up. It is pulling pretty hard actually at the moment. You can see anyway, it actually holds on magnets on the other side. Sorry, the pliers on the other side. Get it in the right position. Oops. But it's still pulling anyway. But anyway, it's worth showing you that. There was a video, I'll try and find it. I'll try and find the video that I did if I can, but I've made that many videos, I've lost count, lost track. Right, anyway, I think that's it for now, because can't think of anything else to show you, so I'm going to end the stream now. Thank you for watching.